Sure. Hello, everyone, and thank you for joining us today. Matt and I are going to be discussing the application of drawing models within Dynochem for the isolation of intermediates and API. I'm going to start the project off with the motivation for the project. Going to touch on resources for drawing development and characterization within Dynochem. I will give a brief overview of the Schlunder method, and then I'll hand over the presentation to Matt, who will go over workflow for drawing development and characterization at Nalis, agglomeration potential, drawing kinetics profiling, the development of the dynamic drawing models, and then I will wrap up with project outcomes and impact, and a comparison of the model predictions to plant results. So like many of the situations that prompt our use of Dynochem, for this project we had a concern around the tech transfer of a manufacturing process to a new site. This method is based on heat transfer as the rate limiting driver for the progression of drying. A couple of unique things that Schlunder did was to employ a resistance to the heat transfer presented by contact of a porous solid bed with the heated surface, and using this resistance separate from a heat resistance for heat transfer through the bulk wet solid. Another thing that Schlunder does is he introduces a mixing number to describe the random motion of particles during the agitation periods in the dryer. There are some very important assumptions that are made in this model that need to be considered, and these are all called out on the Start Here page in the model when you download it.
To evaluate the potential for losing desired particle properties, mostly through agglomeration, as Andrew had called out earlier. This can have a direct impact on both the thermal conductivity of the cake as well as the first layer, the heat transfer, depending on how it behaves in the reactor or in the agitated filter dryer when you start agitating. So oftentimes what we'll do here is at the beginning we will do a filtration testing and agglomeration testing to then determine the severity of the agglomeration. And depending on if there's a risk, ideally it would be free-flowing powder, and we'd go right into our standard drying protocol. But if you do find that you're getting a large degree of agglomeration with a high friability, you'd like to look at either, if the alternative solvent is an option, looking at possibly switching to a solvent where agglomeration is not so prevalent. If you're not able to swap out to a different solvent, then identifying a critical moisture content that you should probably dry down below so as to minimize agglomeration. And then this can be done by increasing either centrifugation or nitrogen blowdown to kind of get rid of as much moisture beforehand before starting your stirring strategy. And when that was then extrapolated over to a agitated run where we dried for about 40 minutes and then turned on the agitation, we saw that the loss on drying and the model agree very well. So the values for this particular heat transfer and thermal conductivity seem to transfer between both a static as well as a agitated run. And that was also the case for the second compound, compound B, where the static and the dynamic or agitated run agree well with the data. Now, as you carry forward to the other compounds, we start seeing a little difference. So compound C, again, agreed relatively well with the data, with the static run and the agitated run giving a little difference at the end. But in the case of D, which was this compound here where I called out that kind of pulled away from the wall as it dried, compound D, the static run fits the data relatively well, but what we see is this pulling away from the wall gave us a heat transfer coefficient for that first boundary layer that's actually incorporating the heat transfer of those air gaps. So it's overly poor, artificially so, because of that air that's now exposed around the wall and the poor contact with the heated surface.
times for the validation runs at the new facility. Fortunately, we were able to get away from those end of shift holds after 8 hours, and they were able to run the dryer on a 24-hour basis. So these times are going to be a little bit lower than those original simulations Matt had shown. And you'll notice here for compounds C, D, and E actually quite broad ranges for this bracketing, and that's really due to with and without the surface area of the base plate. So for these really either low fill volume or high bulk density cakes, adding that surface area from the base plate is actually very significant because of the low cake heights and the small contact area with the walls there. So we, from the conservative approach, we did, have large bracketing ranges, but based off the actual drying times and being consistently towards the low end of these ranges, I think we can conclude that we do get very effective heat transfer from that base plate, and we can include that surface area in any future simulations that we perform for the drying of these compounds.